In this lesson, we're going to deal with the questions related to density and the common concept related to that. And one question that generally troubles the students because it's difficult to solve. So we understand that density is equal to mass by volume. But a new formula, we can say another formula would be of average density. That would be actually equal to total mass divided by total volume. Now, this formula would be used when you have two mixtures or two liquids being mixed together, which do not react with each other, so the total volume remains the same, or just simply being added together. So one of the formulas will be density, simple density, and one of them will be average density. We'll see how to solve the questions. Okay, so moving on, this is the question that troubles students sometimes. So we're going to solve this in terms of density. Now first realize that this is a crystal and there is an arrangement of the crystal and atoms are placed at a certain distance away from each other. He says that the mass of each atom is this much and the density of the crystal itself is this much. What is the shortest distance between the centers of two adjacent atoms? Now, if you go towards the simple approach, you would realize that if you just count the number of atoms in this cube, they will come out as 27, right? But there's a problem. The problem is that if you zoom in, let's say, if you zoom in, you can very clearly see that this is not something entirely related to the distance. You see, if we assume or if we just try to observe this one single atom on the edge, we realize that the sphere's distances are measured from its center. So the entire sphere is not a part of this crystal. Similar thing happens with this one, and with this one. Only the atoms that may exist at the center, for example, this one, are actually really inside this square or cube. So the problem lies with this visualization that is this whole atom a part of this cube or the whole cube itself? It's not. So for simplicity, what we're going to do, we're going to just consider one cube of this whole system or from this whole system and try to see if we can solve the system in that way. Now, when you visualize that, we realize that we come down to this problem. We come down to this idea that it looks like that from this one cube, on the edge of each cube, the sphere or the atom which participates or which is a part of that square actually looks like this, right? So we can see that it's approximately 1/8 of a sphere. This is actually 1/8 of a sphere on each corner. So 1/8, 1/8, 1/8, 1/8. So 1/8 on each corner. So how many corners are there? So we can count them. So this is 1, 2, 3, 4, 5, 6, 7, 8. So we can see that inside one single cube, if we assume this one single cube in existence, we can see that in one single cube, there are 8 pieces or 8 parts of one atom, which are actually 1/8 of another atom that may be, of course, if we complete the sphere, that is going to be a part of another cube in that matter, right? So really, this is just one atom inside this one cubic space, right? So then we use the formula for density is equal to mass over volume. Since we want to find the distance, I believe that we need to find the volume. So making volume the subject of the formula, and mass of the atom is only going to be the mass of one atom, which is already given to you as 3.5 minus 25. So 3.5 into 10 to the power minus 25 kg mass divided by the density itself, which is 9.2 into 10 raised to the power 3 kg per meter cube. When you solve for volume, this answer comes out as 3.8 into 10 raised to the power minus 29 meter cube. Now, since we assumed that this one atom actually is now a part of that one cube, or it actually consumes the space of one cube, this volume is in 3 dimensions, like this and like this. So if you were to find out the distance to the next cubic atom, to the next center of the atom, let's say as shown in this diagram, as we can see, for example, that right now we are just discussing this, or we are just visualizing this one cube over here. So if we were to assume the distance from center to the next atom, then definitely we need to find the length of one of the sides. So in order to do that, we can take the cube root of this value, then you can find that the length, breadth, height, breadth, and length probably, if you can visualize it like that, is going to come out as a single value. So when you take the cube root of this value, the length, breadth, or height, or width, however you want to visualize this, comes out as 3.4 into 10 raised to the power minus 10 meters. Yep, like this one. Okay. All right. So that means that this one length, and this one length of any side of the cube is uniform. We are assuming it to be that way because the density is assumed to be uniform. So that's the length of one side. So if you take it in terms of this cube, let's say this is that cube, then this length is 3.4. This length is 3.4. And if you take the center, that would be half of that length, right? And if you take the center of this one, that will again be half of that length. Again, from center to center, this will come out as exactly the same length again, right? So that is how we're visualizing it. The distance between the adjacent centers, or the centers of adjacent atoms, is going to come out as 3.4 power minus 10. I hope that we understand it in terms of visualization and diagram. So this question was related to density somehow. That's why I solved in this video. Something similar you will see in this question as well, right? So we see that he tells us that initially the distance was 15 nanometers, and if you increase the temperature, we know that due to thermal expansion, the distance between the atoms is going to increase. So now it's 17 nanometers. Now, for the sake of comparison of densities only, we need to realize that the formula is density is equal to mass over volume. Now, when we increase the temperature of this crystal or cube, did we change the mass? No, we did not. So we come down to this relationship that density is inversely proportional to volume. Now we can understand that if you increase the volume, why have you increased the volume? Or how can we deduce that we did that? Is because the distance between the atoms has increased. Now, previously, if they were taking 15 nanometers of space, or distance between the atoms, now they take 17 nanometers of space, which means the distance between them increases, which means that now today, they will occupy a larger volume. So yes, volume is going to control the density. Mass is not, because we did not change the number of atoms, right? So using this equation, we can see, or for the sake of comparison, we can see that the density of new system should be equal to, or in comparison to, the density of the old system. That is going to look something like that, because since it's an inverse proportionality, we can see that this is 1 over V new divided by 1 over V old, or initial situation. So when you put in the values, it's going to look something like so. The density of new system divided by density of old system equals to 1 over 17 whole cube, because volume can be calculated only by multiplying these three lengths, divided by, I'm ignoring the nanometers because in the numerator denominator you get the same answer, so it does not matter, divided by 1 over 15 whole cube. When you solve this now, you may find problem, or you may encounter problem arithmetically doing this. So what I would suggest is use a calculator and the fraction symbol to solve this and get by this problem. So when you solve this, this comes out as density of new ratio with density of old system comes out as 0.6869. If you do this fraction correctly with the cubes and fractions, which will come out as 0.69, which is option B. This is the question that we generally see, and you will find this many, many times over. And this is the formula that is used to solve this type of question. So here we have a mixture, right, of water and glycerine. They don't mix together. He says that some water is added to the measuring cylinder and its volume was 40 for glycerine, right? And the density of the mixture is 1.1. So the average density is 1.1. Now assume that the mixing process does not change the total volume. This is important because we need to understand, we need to accept that they don't react with each other. If they were to react, they may release a gas, they may make a volume or a liquid that has lesser volume, which may change the density somehow, right? So we are assuming that the total volume does not change, which means that they are not reacting with each other. So he says, what is the volume of water that needs to be added into the system? So given the densities of water and glycerine, and the volume of glycerine, how much water should we add so the combined density becomes 1.1? So that's the simple question. So average density, the formula calls for the total mass contribution by both liquids divided by the total volume contribution by both liquids, right? Okay, so for mass, we have density is equal to mass over volume. So let's bring volume over there. This becomes mass equals to being density into volume. So really, this would be density multiplied by volume plus density multiplied by volume. So one of them will be for water, one of them will be for glycerine, divided by the volume of water plus the volume of glycerine. So we understand that the density of water is 1 and glycerine is 1.3 and the volume of glycerine is 40. So density of water multiplied by volume of water, which we don't know, so let's assume that variable to be V, plus density of glycerine multiplied by volume of glycerine, which is 40, divided by the volume of water that we added, which is V, plus the volume of glycerine, which is 40 given in the question. Now, all of this should be equal to 1.1 because he told us that the density of the mixture is 1.1. Now, you have an option to solve this in terms of algebra. You can bring this over here and then multiply and open the whole bracket and solve it in terms of simple mathematics. Or what you can do is you can try every option A, B, C, and D, make a function on the calculator with variables, right? And put each of the answers in this equation in place of V. You will realize that only option D gives you 1.1. So this technique is going from answer to question, right? Or if you want to solve it with algebra, be my guest, it's up to you. But I believe that the thing that I've discussed just now, going from answer to question, saves time. So when I put 40 in place of V and V, my answer for density comes out as 1.15, which is wrong because I am expecting a value of 1.1. So I will reject this answer. Again, doing the same idea, implementing the same idea, doing the same process again gives me density as 1.14. Again, wrong, I will reject this. Density given by the option C comes out as 1.13. Again, I'm looking for 1.1. Now, when I put an 80 over here in this situation, in this equation, I get the density to be exactly 1.1. So my answer should be option D. Next part is not entirely a part of density, but a part of O-levels and GCSE in terms of the topic of kinetic model of matter. So in this topic, we are going to discuss the question of Brownian motion. I will show you a small animation for that matter. So I hope you can see this on the screen right now. This is how the atoms of a liquid were observed under a microscope to be moving at all times, even when at a constant temperature. Now, if the temperature is constant, particles should be stationary or they shouldn't be moving. But now, today, we realize that temperature controls the speed of the molecules or the speed of movement of the molecules. And we can see that the atoms of this liquid are moving, which means that they're being bombarded by other liquid particles present in the solution, right? So this idea is implementable on gas particles. This is also acceptable for fluids that such as liquids. And the same idea and logic is applied on solid particles as well, right? So keeping that in mind, we can very easily see that how this topic will be, or how this question will be solved. He says that in Brownian motion, right, transparent curve filled with smoke, he's doing the experiment with air particles. I showed you an animation with liquid. It's the same thing. So he says strongly illuminated by light. It can only be seen when you apply very bright light. As you might have observed that when you're sitting close to your window, under the direct sunlight, you see dust particles moving in front of the window. That's exactly what Brownian observed at the time. We need bright sunlight so that those smoke particles, which we cannot see with our eyes, get to be illuminated, so that bright sunlight falling on them causes them to illuminate. Or you can say they become visible to our eyes at least. So the air particles are colliding with the smoke particles. He says what can be seen. Now, can we see the air molecules themselves? No, we can't see them. That's why this experiment was conducted, because we couldn't see the air particles. We could only see their effect, that they're colliding with the particles that we can see. And because of their behavior, we deduce that what may be happening with the air particles. So colliding with a smoke particle, this is happening, but we can't see it. We cannot observe it. Air molecules moving in, again, we can't see the air molecules themselves because it's transparent. We can see the smoke particles, yes. Are moving in random zigzag patterns, yes. They're moving in straight lines, no. We deduced that the air particles would be moving in a straight line between the collisions. What we can see is that the zigzag pattern, because of the collision of air particles, which are transparent, and they cause the smoke particles to move in a zigzag pattern, as shown in the animation. Moving on to the next question again, these are the particles represented by the Brownian motion again. Now he says, which box contains the gas with the highest density and the lowest temperature? Now temperature is proportional to the speed of the molecules. This is taken from kinetic model of matter, right? That if you increase the temperature, the speed increases. So he said that the arrows represent speed. If I'm looking for a lower temperature, I should be looking for a lower speed atom. So I can see that because of this simple speed logic, option A and B should be cancelled because their arrows are considerably longer than C and D, right? Now, if you have to make a choice now today between C and D, for the sake of density, we should be looking at particles with even smaller speed and increasing numbers. You see, at the lower temperature, I can see that some particles are not even moving in this system, which means that it's the lowest temperature. And again, the average, on an average, the arrows in this diagram are a bit longer as compared to the arrows in this diagram. So the best option would be option